Most wonderful good afternoon. Good afternoon. Good afternoon. Good afternoon. Good afternoon. Good afternoon. Good afternoon.
Yeah, it's been raining quite a lot in the last month. We're in the north of England, they had some places they had 1 month's rain one day. So they had flooding in a place called Fishpool near Doncaster. And so
Good afternoon.
go there and say, oh, we need better flood defence.
Good afternoon. Good
We
afternoon.
went out for 6 days, so we all said to him, why are you so low? You should be here before.
Most are wonderful good afternoon. Good afternoon. Good afternoon.
Completely dwarfed the election. Anything happened with the elections, secondary news after Prince Andrew. Have you heard that he's given up his royal duty?
But I was joking about the whole thing, and then like now it's like
Which the Labour leader pronounces Epstein because it's Jewish.
Most wonderful good afternoon.
So,
Good afternoon.
hello.
Most wonderful good afternoon.
so we don't want anything more to do with it. We give up our
Good afternoon. Good afternoon.
stand down. All I have to share around.
Good afternoon.
The University of Huddersfield.
Good afternoon. Good afternoon.
And there was this person who was on this TV program, very and dressed program, and she accuses all of the people. So she had a T-shirt on, she's drinking, saying Jeremy
Good
Corbyn,
afternoon.
anti-Semitic, Deborah. So all these people on Facebook say she should be sacked from the program after expressing this view.
Good afternoon again.
I'm in and out these days.
Good afternoon. Good afternoon. Good afternoon. Good afternoon. Most wonderful good afternoon. Most wonderful good afternoon. I like the chicken wing. Good afternoon.
I was waiting for most wonderful you.
Most wonderful good
Thank you.
afternoon to all of
wonderful
you,
good afternoon to
lovely
you too.
people. Thank you. Good afternoon. Most wonderful good afternoon.
And same to you.
Thank you. Good afternoon. Most wonderful good afternoon. Good afternoon. Most wonderful good afternoon. Good afternoon. Good afternoon. Good afternoon. Most wonderful good afternoon. Most wonderful good afternoon. Good afternoon. Good afternoon. Good afternoon. Good afternoon. Most wonderful good afternoon. Most wonderful good afternoon. Good afternoon. Good afternoon. Good afternoon. Good afternoon. Good afternoon. Oh, I wish, yeah. The sofas are very inviting. The sofas are very inviting. Yeah. Most wonderful good afternoon. Good afternoon. Most wonderful good afternoon. Good afternoon. Are you not cold?
No, people keep asking me that, but I feel okay actually.
Fair enough. Good, good, good. Good afternoon. Oh, go back. Good afternoon.
I've got a question. So you know those the results that we got back from those tests that we did the practical. I did pretty shit in the graph one. So I'm just wondering. Is there any kind of review or stuff that I could go over? Do we get the actual paper back?
It's in the teaching lab,
Okay.
but I haven't written anything on it because you've got my email. What do you mean review?
Just to go over what could have done better and what I should
It
have
should
done.
be in the email.
Okay.
Did you read the email?
No, I did. You gave me the marks for the calculations that was
Yeah.
already laid out, but the actual graph. I'm
There's a
not sure.
link in the email
Yeah.
that shows you what the graph should look like.
Okay. I'll have a look.
Compare it.
Alright, thank you.
Okay?
Cheers.
Good afternoon. Good afternoon. Most wonderful good afternoon. Good afternoon.
Good afternoon.
No beans? No beans?
I had cereal before I came. I'm very tired. Can you go like slow today?
Slow.
I was at a gig last night and I'm very tired.
Was it good?
It was really good.
I'm
And
pleased
still
to hear
here.
that. Yeah,
I
yeah, I
couldn't tear
feel
myself away from you.
I feel very honored.
You should.
I know, I know. Okay. Most wonderful good afternoon, ladies and jelly beans. I can tell it's going towards the end of term because the attendance is sort of, there's a slight decay in the attendance. I don't know whether this is a first order decay or something like that, but would be interesting to figure that out. So here is the program, what I'm sort of thinking about doing with you today. I have been asked to go easy on you because it's Friday and some people are still suffering from the Wednesday hangover and things like that. Obviously not you, but you know. Okay, so last week we started with the topic of kinetics, and in this we started off with basically writing a general rate equation. So for example, if you have a reaction where you have reactant A, which is consumed, we can write the general rate equation, the change in concentration of A per time unit. That is how we would write a rate. The velocity of the reaction equals, now we know that the reactant is consumed, so we indicate that with a negative sign, negative rate constant K times the concentration of A to the power of m. And I told you the rate constant is always positive. It cannot be negative. It can be 0, but that is not really terribly interesting because then nothing happens. The order, rate order m, can be any number, whatever you want it to be. It can be a positive number, negative number, and it is just simply a mathematical concept that allows us to write this rate equation. And it's not, doesn't tell you anything about how many molecules interact. It's, as I said, it's just a mathematical concept. I then showed you how we can actually determine this rate order. And I told you that all we need to do is really, we need to take the absolute of our equation. The absolute just simply means we ignore any signs in it. We don't worry about the negative sign. so everything is positive, or in my phrase, life is good, if everything is positive then. And I told you what we can do is we can write this as the logarithm of rate equals m times the logarithm of the concentration of A plus logarithm of the rate constant. And this gives us the equation for a straight line. Y equals mx plus c. So we can very nicely and easily plot this thing. So on the y-axis we plot log rate, and on the x-axis we plot log concentration. And we then get something like that, for example. And our gradient of this line would be our rate order m. And we will need to discuss a little bit about how we deal with, for example, straight lines in some kind of correlation analysis. But that is something that we do next week. It might look rather deceptively simple when you have a straight line. But next week I will demonstrate to you that there is a little bit more to it. So watch that space. And you will need that. You will definitely need that because every good scientist needs to be able to, well, to analyze straight lines. But as I said, next week more about that. Okay, so that is how you can figure out rates, and usually you can tell in an assessment or in a test what I want if the data are given, for example, as concentration of A and rate. If you see something like that, then there is a pretty good chance that I want you to identify what is the actual rate order for this reaction. Now all you need to do is you just simply calculate log A and log rate . This bit here, and you plot it, find the gradient, and life is good. Sorted. No further problems. Okay? That was one thing that we did. We then moved on and said, let's look at special cases. Let's look, for example, at the case where our rate order equals 0. If we have this reaction, A is consumed. And we said we can write this as dA over dt equals minus K times concentration of A to the power of 0. And anything to the power of 0, of course, is 1, so I can easily write this as negative k. And I showed you how you can actually deal with this differential equation. This is where a few people started to hyperventilate, because you would need to integrate that. Don't panic. I'm not going to ask you to integrate anything in a test or exam. I just wanted it briefly mentioned because there are people here who have done calculus and who want to know how you actually do that. You can get this integrated form for this equation as the final concentration of A, and I'm just simply too lazy to always write these square brackets. I mean, if you are on a keyboard, it is a, well, if you are on an iPad or something like that and you try to type that, this is a pain in the proverbial, because you are always shifting and changing key. It's just a nightmare. So please forgive me if I just write AF. That means the concentration of A at the time point that we want to look at. AF minus A initial, that is when we start the reaction, when we look at the observation, equals minus K times T final minus T initial. And I promise you, the week after next, that will be week 11, I think. Is that week 11? Yes. Week 11, we will do, in this workshop, we will do some exercises and calculations where I show you how you actually do these calculations, do these this data analysis from real life data, from data tables, for example. So you won't miss out. And so that is our equation for a zero-order reaction. I told you zero-order reactions are typically found for elimination reactions. So if your body has to deal with some kind of drugs, and I'm not necessarily meaning, illegal stuff. It could be anything. Drugs or certain metabolites. It's not uncommon that they follow a zero-order reaction. We also said that, bless you, we can convert that into the equation for a straight line. So if we plot the concentration of A on the y-axis versus time on the x-axis, we would get a straight line. Oh, it's not too bad, actually, the straight line. I'm pretty impressed with myself. This line represents the concentration of our reactant. It cannot go negative because you can't have a negative concentration of something. Would not make sense if it goes into the negative range. Intercept with the y-axis, that indicates our initial concentration. And the gradient, of course, indicates our rate constant K. And that is what it looks like. Can it ever reach 0? Absolutely yes. It can reach 0 when all A has been consumed. The unit for the rate constant here would be concentration per time. So if you see concentration per time in a rate constant, you know it must be a zero order reaction. Okay, we then moved on swiftly to a first order reaction. Again, we start with a reactant A. And we wrote the rate equation for first order, dA over dt equals minus K, because we have a consumption, times the concentration of A, and this time to the power of 1, which is indicative of a first-order reaction. Where do we find first-order reactions? Again, very common. It is the elimination of metabolites or drugs from the body, and we also find it in radioactive decay. Radioactive decay cannot do anything else but first order. So whenever you hear the word radioactive, you know by default it is first order. Can't be anything else. The physics is not that advanced that radioactivity can do anything else but first order. We integrated this equation and we ended up with the integrated form for that. Again, you don't need to know how to do this integration, just for those who want to know. And we get the natural logarithm of the final concentration of A minus the natural logarithm of the initial concentration of A equals negative K times T final minus T initial. And I told you we can write this slightly in a different format because the natural logarithm isn't everybody's cup of tea. Am I right? Yeah. You can, under the laws of logarithm, you just simply can put them together. Natural logarithm of A final over A initial concentration equals minus rate constant times T final minus T initial. And if you want to get rid of the ln altogether, you just simply E both sides and you get A final over A initial equals E to the power of minus K times T final minus T initial. If you are asked to represent a first order reaction graphically, what you would see is if you plot concentration versus time, you would get a curve like that. It is asymptotic to the x-axis, which means it will never ever reach the x-axis. So it will never ever be totally zero, not like the zero order reaction. However, if you want to avoid a curve like that, what you can do is you calculate your natural logarithm, and instead you plot the natural logarithm of your concentration A versus time and you get a straight line. The intercept here would be a natural logarithm of your initial concentration, ln AI, and the gradient would be, again, your rate constant k. And in this case, the graph can go into the negative area just simply because ln of a number can be something negative. It doesn't mean that the number is negative. The number is just smaller than 1. Then it can go into this negative range. The unit for the rate constant in this case would be 1 over time, or time to the minus 1. Okay, happy with that? This graph, this time, if that gives you a straight line, it is indicative of a first order reaction. And if you are ever asked to demonstrate graphically that that a certain reaction is a first order reaction, you just simply plot this ln, natural logarithm versus time graph. If it's a straight line, you know first order, sorted, life's good. We also discussed in this case the concept of a half-life, T half, and we said the half-life is defined by natural logarithm of 2 divided by the rate constant. So if you've got a half-life, you can convert that into a rate constant and vice versa. So very often when you're looking at radioactive decay, people don't usually give a rate constant, they give a half-life. So a half-life of, for example, the radioisotope 32 phosphorus is 14 days. With this knowledge, all you need to do in order to get the rate constant is just simply rearrange this equation, and you get your rate constant. Problem solved. Happy with that? Yeah. We then discussed the case of what happens if we have 2 reactants, A plus A. This is a typical scenario when we have the dimerization of a receptor. Many receptors on the cell surface need sort of a phosphorylation event. They bind a ligand, they bind the ligand, then dimerize, and once they have dimerized, they can sort of cross-phosphorylate each other. You probably have seen that in one of the cell biology module. No? Sort of? Well, actually, that is what happens. We can write this as a rate equation, dA over dt equals negative k times A, concentration of A, to the power of 2. Indicative that this is a second order reaction. And I told you that the integrated form of this rate equation would be dA, oh, sorry. It would be 1 over A final minus 1 over A initial equals K times T final minus T initial. And just to make sure we are on the same page, in this case there is no negative sign in front of the K. That is a sort of, that happens when you do the integration of this particular thing. So don't worry, it's not a typo. Deliberately there is no negative sign in here, in front of the K. And we said we can plot this. We plot time versus 1 over A. And we get a straight line the intercept is 1 over A initial. And the gradient, again, is our K, our rate constant. Unit for the rate constant in this case is 1 over concentration times time, or concentration to the power of minus 1, time to the power of minus 1. So if you are asked to demonstrate that a reaction follows a second order reaction, you plot 1 over the concentration versus time. If it gives you a straight line, you know it is a second order reaction. And I think that is where we stopped last time. So let's have a little bit of fun with a little bit more stuff. We said that is a second order reaction. And it happens quite often, but even more often we have a different kind of second order reaction, or general different reaction. We have the reaction A plus B gives something. So in the previous example, our reactant was sort of identical. Now we have two different reactants. Let's see how we can write the rate equation for that. So we can write the change in the concentration of A per time unit. Obviously, A will be consumed. What would be the sign that we have here? Positive or negative? If it's consumed, must be negative, exactly. Minus rate constant K. Now, does the speed of this reaction depend on the presence of A in this case? Do we need A for the reaction to happen? Yeah? Good. So let's write that very general as concentration of A to the power of M, because we don't know what the rate order will be. Now, does the speed of the reaction depend on the presence of B? Yeah? Absolutely right. So times the concentration of B, and let's just simply call that rate order N. So here we have our general rate equation. This is the equation for how fast our A disappears. What about B? dB over dt equals, what is the sign? Positive or negative? Is it consumed? Sorry? Yeah. Yep, you're right. Minus k. Does the disappearance of B depend on A? You're right. A to the power of m. Does it depend on the concentration of B? Yes, it does. B to the power of n. You see, it's exactly the same rate equation, because both need to act and interact with each other and then are, disappear. So we can actually write, in this case, dA over dt equals dB over dt. It's exactly the same speed. There are no two speeds for the two things. Disappears in a similar way. By the way, we can actually say the overall rate order for that is just simply m plus n. That's the overall rate order. We would say the overall rate order is m plus n, and this reaction is of the order m with respect to A and the order n with respect to B. And together they are m plus n. So for example, if m is 3 and n is 2, we would have an overall rate order of 5 with rate order 3 for A and rate order 2 for B. That is how you would describe it. Okay, happy with that? Now, let's integrate this, or let's just simply, first of all, let's make things easier. Let's do an overall rate order of 2 and say we have dA over dB dt, which is of course the same as dB over dt, equals minus k times A times concentration of B. So overall rate order is 2, and the rate is first order for A and first order for B. Let's integrate that. Actually, let's not integrate that. Integration of this thing is an absolute pig. And you end up with an equation, and although this looks totally innocent, you end up with an equation that goes over 2 lines. I have to look it up. I can't remember. Life is too short to remember something like that. Yeah? If you can look it up, don't bother with it. So I will never ask you to do that. And scientists who have to deal with that, usually, they turn autumn blonde. And no, I'm not grey. These are just stress highlights. So if you have to deal with something like that, there is a nifty trick what you can do. Obviously, A and B would disappear at the same time. Now, the trick is, if you make the concentration of B much, much, much larger than the concentration of A, then something weird happens. So for example, we have A 100 and B we have 1,000,000. Now let's say in the first step we make 10% disappear, 10% of A. That would be 10 disappear. How much of B would be consumed in this reaction? Think about it. For each A, we need one B. Don't be fooled by the 10%. How much of B would disappear? 10. Why not 10%? You're absolutely right. It needs to be the same number as A. So we have 900,000, 909, 999, 990. Which is damn close to the 1,000,000 that we started with in the first place, isn't it? So what we are doing basically here is, it's more or less, B stays more or less constant. And even if all of A was consumed, we would still have 999,900 of B. So B does not really change. So that means if B doesn't change really in this case, we can say B stays constant. And B actually, if it is constant, we can put that into our rate constant. So we can write dA over dt equals minus K, and I give it a little sort of dash or prime. That indicates this is nothing else but K times B but it stays more or less constant, times A to the power of 1. So what order is this guy here? What order is this equation now? Loud? It's a first order, you're absolutely right. And yet it's not a first order because there was a B before that. So therefore, this trick has a name. We converted the reaction into what is called, it's a pretend. It's a pseudo first order. It looks like a first order, but actually we could do that only because we made B very, very large so that the disappearance of A doesn't really count in this case. So it's a pretend first order. Make sense? And you will find that fairly often. If people don't want to deal with the pig of equation, you make B very, very large so that it almost stays constant. And nothing changes with that. pseudo first order. Makes life so much easier. Sorry?
Is the like symbol next to the K just power of 1?
This one here? No, that is what I want to. Oh, okay. Let's do that slightly different to make it clear. Let's give it a star. This just simply means this rate constant is now a sort of a composite rate constant of our original rate constant and the concentration, the high concentration of B in it. Because B doesn't change. So that's a sort of, usually you wouldn't even find that indicated in a different way, but I just wanted to do that here to indicate, yes, it is not any longer our original rate constant, it is with B added to it. But good, thank you for pointing that out, Alex. Okay, so we now know how to deal with two reactants or substrates. Now let's have a look at actually what happens to this stuff when we have a reaction. We have sort of always just said, oh, A disappears. Yeah, but what happens to it? I mean, what happens to the chocolates that I ate? I don't want to tell you in very graphic terms what happens to it, but yeah. So if we have a reaction A to P, and here A is our reactant or substrate, and P is a product, whatever this product is. How does it look like? What do we need to do? Let's write our rate equations. dA over dt. A consumed, yes or no? Yep. Sign? What sign do we need? Negative sign minus K times concentration of A to the power of M, if we are very general. Cold coffee, we've done that 100,000 times. What is the rate equation for P? dP over dt equals consumed or produced? Produced. Sign? It's a positive sign. Rate constant. Does the production of P depend on A? Yeah? Absolutely right. The rate equation for the product formation is positive K times A to the power of M. You might say, Master, that's a bit weird, because shouldn't it be P, concentration of P? No, it's not. It depends on A. We will come across later today a reaction where it depends on P, but for the time being, we are not dealing with that. So, we could, of course, integrate that, but this last bit to integrate is a little bit tricky. But we can deal with a different trick that we can do. And at least Alex doesn't have to hyperventilate when integral comes into. Sorry, I have to take the piss. What we say is, let's just simplify what's going on with this reaction. We plot, say, concentration versus time. Let's say we have something like that, and that is our A. So our A is consumed, and that is our A initial here. Now what does B look like? Let's assume we have no product there in the first place. What does P look like? It would look like something like that. That would be our product P. Make sense? And what we can say now in a case like that is, if we look at it at this time here, we can say the product at that time and the reactant at that time together will always give us what we had at the beginning. And I can write that as A final plus P final is always what we had at the beginning. Things can't disappear. Make sense? Hope so. So, can we calculate our P final? P at a certain time? Well, we can, otherwise I wouldn't do that with you. We can rearrange that and can say P final equals A initial minus A final. Or if you like graphically, in order to get this guy here, all we need to do is we take this one here and subtract this one from it. Well, we can not only do that graphically, we can also do that mathematically, because we know very often we can write A final, we can calculate that. Let's just simply say we have a first order. So dA over dt equals minus k times a to the power of 1. We know that in this case, A final equals A initial times e to the power of negative k t final minus t initial. That was one of the equations that I showed you earlier in the revision part. Right, so all we need to do is we just simply plug this in here. And we get for our final product concentration equals A initial minus A initial times e to the power of minus k t final minus t initial. Or I can write this a little bit nicer, and I can say this is A initial 1 minus E minus K T final minus T initial. And the shape of that, as I said, would be just a simple curve like that. You actually don't really need to learn this equation by heart because it really follows from everything else. You look skeptical?
I mean, it really follows any.
Oh, it does follow. It follows. It's total logic. That's the beauty of maths. Yeah? F the beauty of maths. Yeah, I know what you're thinking. Maths can't be beautiful. Maths is beautiful. It's gorgeous. It's sexy. It is, wonderful. I want you to appreciate maths. Okay, maybe not. That makes sense. Sort of. Now you can calculate not only how fast A disappears, but you can calculate how fast P, the product, is produced. Gorgeous. Wonderful. How are we doing this time? Okay. Our next thing that we need to look at is, so far we have discussed A disappears and it produces a product, and for a reason that I will elaborate in a little bit later, let's just simply call it B. A is converted into B. And B is converted back into A. This is a reversible reaction. Previously, we only dealt with irreversible reaction. It goes only in one direction. Actually, it would be a name for a band. One Direction. I think that would be a good name for a band. I should probably sort of patent that. Now, things go in both directions. How cool is that? How are we going to deal with it? To be revealed after the break. 7 minutes break. What? Sorry?
He has pizza.
He has pizza. I think that's not a reversible reaction, eh? Actually, you are aware that you are not allowed to eat in here.
You can have a slice if you want.
That's a good bribe, though. That's a good bribe.
Absolutely.
No.
Have you been good?
Actually, he has been paying attention.
Yes, I can.
What kind of pizza is it?
Chicken supreme.
Chicken supreme.
It's like you want
As long as it is not kitten tikka masala.
How can that be a pizza? That's not.
There is companies.
Oh, people do all sorts of pizza. In Scotland, they deep fry pizza.
That sounds so good. No, please.
Yeah.
I mean, unhealthy, but good.
Deep fried pizza?
Yeah.
How does that work?
They deep fry anything. Mars bars.
So that's good.
This year is actually.
It's so good. Have you never had deep fried marshmallows?
They're amazing.
They're so good.
Hold up.
It clogs your arteries and you feel it, but it's good. Yeah.
You have
Yeah.
never seen
And you
Yeah,
put it
you
in
deep fry it.
I've seen the left side from the way.
and that's not deep fried Mars bar. How dare you?
oil. No, it's foreign.
I think it was like 3 variables, and you said if you wanted to integrate it, it'd be too much of a fuss.
You mean this
I think
one?
it might,
This,
that one?
yeah, this one here.
Yeah, so I didn't, because I'm a bit rusty with integration, but I didn't see why it would be that complicated. Why would it be too long?
The reason is you have dA over dt, right?
Yeah.
Now, for integration, you usually have to separate the variables.
Yeah.
So the a goes to that side. That's trivial.
Yeah.
But what are you going to do with the b? B is also a variable.
Because could you just not take them off to the left?
Then you can't integrate.
Yeah, because I suppose the multiplication rule is only
Yep.
right. Okay.
Yep. So this is actually a pig to integrate.
Because we'll think, well,
You can do partial integration,
okay.
or partial integral, where you then just simply say, oh, I treat that as a constant.
Because I was going
Actually,
to say,
it's
could
not.
it not just all be constants? No, you couldn't do that.
No.
Okay.
It's not a constant because it changes.
Yeah, I guess.
You see the problem?
Yeah.
So that there are programs out there that can do it for you.
Like from off and stuff.
Yeah.
Yeah.
But if people can avoid it,
Okay.
they rather go for the pseudo orders.
Okay, interesting. Because I definitely didn't doubt it, but I was just
Yeah,
wondering.
yeah,
'cause I
no,
was
no,
like,
no, no.
yeah.
That is the reason why, you run into a massive issue with that guy, and it looks so innocent. I mean, look at that. There's nothing to it. That's A plus B. It's piss. Yeah. Nah, it's not. And as I said, if you try to integrate it, you end up with a big equation with several logs in it. And it's definitely not something that you want. And then it would only be, this particular case would only be if both were first orders.
Right, okay.
Yeah? If you've got then more complex orders, you rather shoot yourself or somebody else than try to do that integration. You still tired? I thought I might wake you up.
What, with logs?
Yeah.
No.
No, it doesn't excite you.
No, it doesn't really get me going. I'm afraid. It's not really what I find invigorates me.
But at least you're not shaking and panicking about them.
I'm
It's
too
just-
tired to panic. I need a coffee so bad.
Intravenously. They have got one outside.
I don't have time to go home anymore. It's fine, I'll just cry.
I appreciate the problem, yes.
I'll just cry, it's fine.
No, don't cry. It just blurs the vision. It blurs the vision if you cry.
I mean, I'm not understanding any of it anyway, so it's all for me.
Brilliant, love it. I have to say I'm very grateful that we didn't start eating the pizza while I was talking, because usually then I start salivating like mad. This is actually an interesting experiment that you can do in front of a brass orchestra. You know, when they do
Oh, no, he can't do that.
bite into a lemon.
Oh, okay, so it would.
Wait, no, but
You bite into a lemon, they watch you and they can't blow a single tone anymore. It goes like, try it.
where am I going to get a brass orchestra?
Have you tried it before?
It works. Occasionally on a Sunday morning they play at the Dane John's Gardens in the summer.
But they're gonna, then what's going to happen is they're going to see the whole of our cohort just biting lemons
Yeah.
all together.
I mean, you can try that yourself. For example, just imagine some lemons. Just imagine them. You can feel your salivary glands producing. Imagine a lemon. Can you?
I'm a weirdo. I can eat a lemon just like that.
Well, I don't want to comment on the first part of your statement.
It's bad for your teeth, though, so you shouldn't do it often. But sometimes when you just feel, you need to be, awakened in your feet.
Okay, shall we continue? Because I know that, for example, some people indicated in the group chat. It's like a red thing around the brain, right? And the heartbeat is all over the place. I feel really privileged that I can make your heart race. Yeah? So maybe I shouldn't tell my wife. Actually, she might be watching that because occasionally she watches on YouTube the stuff, so I might be into a little bit of trouble. Never mind. Right, here we have a beautiful reversible reaction. Now, how on earth are we going to deal with that? Well, actually, let's just simply take a totally simplistic approach to that. Let's just say, first of all, we have A is consumed. And we know how to deal with that. We can write for that minus k times A to the power of m. If we indicate that this is k, let's call that k1. It's probably easier. K1 times A to the power of m. That is when A is consumed. Let's look at the reverse reaction. B produces A. That's the reverse. Let's call this rate constant K minus 1. The reason why I call it K minus 1 and not K2 will become apparent later on. And we know how we deal with that, because we can say for the production of A, we have plus K minus 1 times B to the power of n. So in one case, A is consumed into B. I can put the B here. And we have minus K1 times A to the power of n. In the other case, it goes in the other direction. We have plus K minus 1 times B to the power of n. So we have sort of dissected that into two half reactions. And all we need to do is now we just put them together. We just say dA over dt, and please don't get scared about that. It just means a change in A concentration over a time period. This is nothing scary. It doesn't bite. Bless you. dA over dt, and we put the two reactions together, equals minus K1 times A to the power of m plus K minus 1 times concentration of B to the power of n. This would be our rate equation for A. And you probably think, WTF, welcome to Friday. What am I supposed to do with that? Why care? Who gives a flying flamingo about that? Actually, you can do something really, really cool with that. Let me show you. Here's a reaction. Here's a similar reaction, a little bit more complicated, but it is basically two molecules. I think it is the yellow and the blue ones. They react together and they form some what is supposed to be green molecule, but it's also a reversible reaction. So this is going to be a simulation of a reversible reaction. As I just said, just there's an additional compound in it, but don't worry about it. Now let's run this simulation. Oh, yeah! You see what's happening? Now, if you look carefully, this bit here, down here, tells you how the reactants and products change. And you see, right at the beginning, we have something like our reactant going down and the product coming up. That is before we reach this very bizarre plateau. Everything is plateaued. Do you see that? That means, although the reactions happen, still happen, on the outset, it looks like nothing else is going on. What do we call this phase? When nothing happens anymore. We are at an equilibrium. Absolutely right. We are what is actually called dynamic equilibrium. We have a dynamic equilibrium. Dynamic because reactant is still converted into a product, but then at the same time the product is converted into the reactant again. So it is dynamic, but it looks like the reaction has reached a standstill. So the rate, the change in the reactant and in the product is basically zero. Nothing is changing anymore. On a microscopic level, yes, a reactant might form a product and the product forms a reactant again, but on a larger level, there is no change in it. So, if we have, excuse me, if we have reached the dynamic equilibrium, we can say dA over dt equals 0. There is no change. The concentration of A won't change, and also the concentration of B won't change in this case. Nothing changes anymore. And yet, we still have this equation there. we still have 0 equals minus k1 times a power of m plus k minus 1 times b to the power of n. This equation still holds, but it's 0. So what we can do is actually we can bring this term here to the other side of the equation. And we get k1 times a to the power of m equals k minus 1 times b to the power of n. Make sense? Well, it's just simply shifting one to the other side. What I do now is I bring everything with a concentration to one side and everything that is not a concentration to the other side. So, for example, I bring a to that side by dividing both sides of the equation. And I bring the k minus 1 to that side. So what I end up with is k1 over k minus 1 equals b to the power of n over a to the power of m. Do you see how this worked? Yeah? Now here's the thing. If you've done chemistry, what do you call this bit here? What do you call that?
Equilibrium is constant, equilibrium constant.
Shout it out. You are absolutely right. Go.
Equilibrium constant.
It is the equilibrium constant. K equilibrium. That is the equilibrium constant for this reaction. If that doesn't blow your mind, you have no emotion. It's one of my favorite phrases. The equilibrium constant for this reaction is nothing else but a combination of the two rate constants. How sexy is that? That can be misconstrued now, but that's absolutely fine. I wasn't offensive, was I? You get an equilibrium constant. Let's do it more sexy. Oh yes, oh yes, oh yes, oh yes, oh yes. Fantastic, thank you. That is the comment that I want to hear. Delta G naught, your Gibbs energy under standard conditions equals minus RT natural log of the equilibrium constant. And now we can write the equilibrium constant in a different format. We can write it as minus RT natural logarithm of K1 over K minus 1. The rate constant for the forward reaction divided by the rate constant of the reverse reaction. And now all of a sudden you have this beautiful, gorgeous marriage of two of the most amazing subjects, kinetics and thermodynamics. Isn't that just beautiful? Amazing. Because what this actually tells you, what does thermodynamics tell you, if you think about it? What does thermodynamics tell you? Why on earth are we teaching you thermodynamics? Yes, I know, you asked yourself that as well. What does thermodynamics tell you? Mm-mm. 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 Thermodynamics tells you whether a reaction potentially can happen, whether it's feasible. Can it happen? And gives you an answer, hopefully. It tells you, yes, it is feasible, or no chance in hell. And when it tells you it's feasible, that's where it stops. It doesn't tell you whether it will happen. It just tells you it is feasible. It is feasible that I win the lottery because I buy a ticket. If I didn't buy a ticket, it would be more than a miracle if I won the lottery. So, thermodynamics tells you, could you win the lottery? Kinetics, on the other hand, says, I tell you exactly when you will win the lottery. So, thermodynamics tells you, is it possible? Kinetics tells you, how fast will it happen? If you have a mixture of hydrogen and oxygen, thermodynamics tells you, yes, it is feasible. Boom. You can store them for 100,000 years next to each other and nothing happens. Thermodynamics says, well, it happens. Kinetics tells you, yep, and I can tell you exactly what you have to do to make it boom. You have to lower the activation energy. That is where kinetics comes in. And here, with this beautiful equation here, you have the marriage of thermodynamics and kinetics. Beautiful. Now, for bioscientists, as we are, we usually don't deal with a simple system like, where is it? Like this one here. Because in a cell, if you have reached an equilibrium, you're dead. In biology, there is no equilibrium. For example, we always have something coming in and something going out. There's no reverse reaction in it. I had breakfast, and 2 hours later, exactly the opposite. So, breakfast in, other things out. There's no equilibrium. I can't turn the, out into breakfast again. Well, okay, let's not go there, right? But it's not that, from an energetic point of view, it doesn't make sense. So what we are actually looking at is something goes in, let's say into B. That's my body. And then it goes out again. K1, K minus 1. Now let's stay with the example of breakfast. If basically I eat as much as I shit, right? I won't put on weight. It's as simple as that. Still stuff going in, stuff coming out, but there's no change. Does that remind you of what we just said 5 minutes ago with the equilibrium? It's like an equilibrium, isn't it? But yet it's not an equilibrium, because an equilibrium is a closed system. You have A and B, that's it, end of. In this case, you have breakfast, you have this one here, and you have this one here. And day in, day out. If the outgoings are more than the incomes, then you waste away. If more goes in than comes out, you expand. If nothing happens, sort of an equilibrium, but not an equilibrium, because it is an open system in this case. And to indicate that we have an open system, this is not called an equilibrium. It is actually called a steady state. Steady state just simply means there's no change. Income is the same as outgoing. Of course, breakfast every day is different. Steady state is nothing else but an equilibrium for an open system. And here we can write the equation for our change. dB over dt equals, well, we have an income that is K1. We don't have an A here, so we can't do that. K1. Oh, by the way, what kind of reaction would that be? Just K1. What reaction is that? Sorry? It's a zero order reaction for that in this particular case, because we don't have an A there. Yeah? K1. And now we take away K minus 1 times B to the power of, let's say, n. So that would be the rate equation for exactly this guy here. Income, that's the first part. Outgoing, that's the second part. And at steady state, nothing changes. We have got 0 again. And we can rearrange that if we're inclined that way. So we would have K1 equals K minus 1 times B to the power of n. So I bring that to that side here. And getting everything sorted and nicely tidied up, I would end up with Bn equals K1 over K minus 1. That actually gives me the sort of the concentration of B, the steady state concentration of B. And again, you see, the cool thing is, it's nothing but a combination of the two rate constants. It's not a miracle. It's just, you just rearrange a few things. So what you see here is we could, in theory, look at rather complex pathways. And for each pathway, we can determine what's going to happen. This could be, for example, the pathway of glycolysis, as we will discover next term. And we can describe that with rate constants. Nothing else. We just need the rate constants and the rate orders. But very often we'll find the rate orders are either 0 or 1, or anything in between. But, we can deal with that. Isn't that beautiful? Doesn't get this you excited? Okay, maybe not. So here we have beautiful steady state. Like Steve Jobs at the Apple conference, I want to give you one more thing in terms of kinetics. Oh, you're flagging. I'm so sorry. Okay, here's something for you, especially for you, because that is a little bit more complicated. No, it's not. What we have looked at are reactions like A to B, for example. A is consumed, B is produced. But B is always, in a way, if you like, constrained by how much A I have. I can't produce B ad infinitum. It's not possible. And yet, sometimes we see that there is no constraint. Let me indicate that in a reaction scheme. This time I use the letter N which some of you might have seen in a different context. N, and actually N produces more N. And I indicate it like that. Typical example, rabbits. You've got 2 rabbits. Let's not worry too much about the biology. Obviously, they would need to be different sex and the right age and things like that. But if you've got 2 rabbits, soon you have more than 2 rabbits. Soon you have even more than 2 rabbits. And soon afterwards, more rabbits and rabbits and rabbits. Yeah? So what you are having here is the typical example of an exponential growth. So how can we write this? Well, just simply dn over dt equals, we have a rate constant, and usually when we're talking about growth, we call the rate constant r. That's the same thing as k. So that's rate constant. The whole thing is positive because the rabbits are not consumed. They produce more rabbits. R times n, oops, what have I done? N, and very frequently this is a first order reaction. N to the power of 1. So the only difference between what we have done before is now we've got the positive sign in here. We can integrate that. We can say n final we get natural logarithm of n final minus natural logarithm of the initial rabbit concentration equals r t final minus t initial, or just cutting a few corners, n final equals n initial e to the power of positive r t final minus t initial. That is nothing else but a growth equation. And if you think about it, for the equation when we have the consumption with the first order, we defined a half-life. Well, we just as well can define a doubling time. For this. And I like to abbreviate doubling time as T2/1. Remember, half-life, I indicated T1/2, that's the half-life. Doubling time is sort of 2/1. And if you do the maths for that, you will find that is another miracle of life of rabbits. You will find this equation to be the natural logarithm of 2 divided by the rate constant. That's the doubling time. Now, what would this actually look like if we plot the number the number of rabbits versus time? We have an exponential function, don't we? Here is number of rabbits versus time. What would this graph look like? Can you sort of do it? Column goes like that. Do you agree? It's an exponential function. It's a typical growth curve, a typical growth function. When will it end? Loud? Never. You're absolutely right. Theoretically, it will never, ever end because we don't have a limitation on it. Does that happen in nature? Does it happen in nature that the rabbits are just producing more rabbits and more rabbits and more rabbits and more rabbits? Sorry? It stops. Ah. So in nature, you would most likely get something like that. N time Have you seen that? Curve like that? That's a typical growth curve for a natural system, for anything biological. It's no longer an exponential growth. It actually has a plateau. Anyone know what this plateau is called? No? Haven't done that in biology? This plateau is called the carrying capacity. And it's usually abbreviated with something absolutely horrible. I can't help it. I have to tell you the truth. It's abbreviated with a capital K. Doesn't mean equilibrium, although it's sort of, if you think about it, it's sort of an equilibrium, because then once you've reached the carrying capacity, nothing will change. This is the carrying capacity of the system. It just simply means our rabbits at the start do what rabbits do. We produce more rabbits. The rabbits, of course, need some space. They need some food. And sooner or later, they have consumed the food. So some rabbits will die. Other rabbits will reproduce again. And we reach this limit. The equation for this curve, this is also, you find that referred to as logistic growth. And I've already sent you in your daily Friday email sort of a little bit about how you deal with logistic growth curves. This is, by the way, this is a typical growth curve of a bacterial culture. It will grow very, very quickly at the beginning, and then it reaches a point where no further growth happens. It doesn't mean that some bacteria still divide, but it also means that other bacteria die, and there is no further increase in growth. So this is a logistic growth curve. And we can write dn over dt in this case equals, and I always have to look it up myself because r times n times k minus n over k. And this part here, r times n, that is what we have said here already. R times n. This factor here, k minus n, divided by k, this tells you basically how far away the system is from the carrying capacity. I'm not going into what happens when you integrate that. It's getting a little bit interesting. But I just want to show you that there is a relevance to it. Because you have different biological systems who have adopted through evolution, through genetics, through BI324, they have developed different strategies to reproduce. You have organisms that are either adapted to reproduce as K-adapted or K-strategists, these are organisms that live predominantly at the capacity of the system. Or you have organisms that can reproduce very quickly. They are called the R strategists. Have you heard about K and R strategists in biology? No? Because I think that's really interesting. R strategists are organisms that produce huge number of offsprings. We are basically, for R strategists, we are in that area of the growth curve. They can multiply incredibly fast. A characteristic of R strategists is they are usually small organisms and they produce thousands, if not millions, of offspring. For example, a very typical example is an oyster. An oyster produces millions of fertilized eggs. These eggs are released into the environment and sort of we pray, as the oyster parent, we pray that some of our kids will survive. Not many. Very few will survive. But actually, if you think about it, oysters don't really have parents because for our strategists, parental care doesn't exist. So, our strategists, small, no investment in the offspring, but loads of them. When would be an R strategy be useful? It would be very useful if you live in an unstable environment. Because you produce so many offspring, you do so much meiosis, you do so much gene shuffling and recombination that hopefully one or two will have exactly the right genetic makeup to survive in this unstable environment. These are the R strategists. K strategists, on the other hand, use a completely different approach. They are usually big animals like elephants. They have very, very few offspring. The pregnancy duration for an elephant, I think, is 21 months. And there is an enormous investment of the parents for the young. They live at their capacity. And the environment is probably very, very stable. Now, if you change the environment, K strategists are truly screwed because they have only one or maybe 2 or 3 offspring. And any changes, they will suffer. R strategists, they say, so what? We produce millions of children, not a problem, in one go. So changing in climate, changing in environment favors the R strategists. K strategists can't cope with it. That's why, for example, many of the K strategists nowadays are endangered. R strategists aren't. Where do humans sit? Humans, K or R? Okay? Okay? Well, it's interesting because I would have agreed with you there are K strategists, but we know, for example, that for some people, children, especially when you are from the Thanet region, I didn't say that. Yeah, there's a city called Pramsgate. The children are seen as sort of a means to get benefits. Really mean of me. No, humans have been seen as K strategists, but there is new research out there which says that they are sort of actually a mixture. There are other factors. For humans, parental investment, most of the time, unless you are from some areas. Low numbers, again, if you are from certain areas, that's not true. But they can cope with variable environments. Do we live at the carrying capacity? Have we reached the carrying capacity for this planet? 8 billion people on this planet. Have we reached it? The maximum? Actually, we don't know. It could be that we are already over, that we are overshooting, and now we are going to crash back to the equilibrium point. Maybe there is enough food, space, resources for 10, for 20, for 50 billion people. We really don't know where we are on this beautiful logistic curve at the moment. So we don't know whether we are K or R. We don't know where we are on that curve. But at least we have fun. Thank you very much and have a lovely weekend.